Complejos and the theorists in mesoscopic physics and complex matter physics in general. He did his PhD in 1984 from Leiden University with the advisor as advisor of Peter Matsur. Then he was postdoc in Stanford, in Santa Barbara, and after that he works in research labs, in Philips research labs in Poland. And since 1991, he is the head, he's professor at Leiden and the head of the nanophysics. Carlo has an impressive list of scientific merits. I just read them from the web page. More than 300 publications, an H index larger than 86, and has had many professional activities, including serving in editorial boards of many journals like Physica, Physical boards, Analogue Physics, New Journal of Physics and Science. He also has a very long list of PhD students. He has advised more than 20 PhD students. He has received many prizes, the C.J. Koch Prize for his thesis work, the Royal Shell Prize for conductance quantization, for the prediction of conductance quantization, the Sistemas Prize, many others. He even received the award of being Knight in the Order of the Dutch Lion. I could continue enumerating the long list of scientific merits, but I think I should better finalize, and I will do that mentioning that the work of Carlo Beenakker and his group has allowed many theoretical predictions. Some of them have been already confirmed experimentally, others are confirmed. I can mention, for instance, the work on the conductance quantization, which I mentioned. Also the prediction of Coulomb blockade in a Hahn effect, the work on shock noise, on graphene, and more recently on Majorana fermions and topological materials, which is related to the colloquium today. Thank you very much, Carlo, for accepting the invitation to present the colloquium, and we will look forward to listening to you.
Very good. This works immediately, or do we have to switch this on? Or
I think it's working.
It works out of the box. Very good. So, it's a great pleasure for me to be here in Mallorca. When I told people back home, you know, the streets are full of Dutch, as you know, right? Really full of Dutch. So when I said people, you know, I'm leaving for Mallorca those days, say, yeah, sure, we'll have fun. Said, no, it's for work. Nobody believes me. Nobody believes me. So that's a big asset which this island has. You work on the vacation paradise. So I understood, I got an excellent overview of the institute from your director, that this is a center of complexity. And I will be giving you a talk about complexity, and I try to aim at it somehow, a physicist, but there will be enough also if you're not a physicist, I hope. And it will be about complexity without complex numbers. That's basically the subtitle. And yes, the Majoranas are there, don't worry, they'll come. And topological superconductivity is there. So that's the idea. I very recently wrote a tutorial for non-specialists on this. It's published in Nature Physics. And Nature Physics did, and actually the entire Nature group did something good. Let me just advertise it at this moment. So they're a bit under pressure, right? Because if you're not a subscriber to any of these glossy journals, you're basically left out. You have to subscribe, which is expensive. You can buy individual articles, which cost $50. It's ridiculous. Nobody does that. And so they're under this whole open access movement. And so they've done something which I think is good. They have created magic links. And I'm not probably allowed to somehow, really distribute it in a massive way, but for audiences like this, and probably the YouTube video is also okay, I'm allowed to distribute the magic link. So this magic link, unfortunately, you see also the good thing, it's kind of short, so you can even kind of memorize it. And particularly because this thing here is just the the hosting service. That's the hosting service of the magic link. So the only variable is this. And you can see that they've just started doing this because there's just only 4. I mean, it will grow eventually, of course, right? But at this moment there are only 4 identifiers. So they've started allowing authors to distribute magic links, and then you can just read it as if you're a subscriber. Isn't that cool? I think that's a good, and I want to applaud them for that. I think it's a good idea. Anyway, so this talk is basically somehow extracted from that tutorial which I wrote with Dale Cowan. So first, a little bit about quantum mechanics. I checked with my host that most of you have had, all of you, most of you, have learned some form of quantum mechanics. And it's a weird theory. And it was already a weird theory when it was first developed 100 years ago. And one of the weird things is that Erwin Schrödinger, who wrote down the first equation of quantum mechanics, this was a complex equation. I'm sure you know the Schrödinger equation, right? What is it? I always have to forget whether the I is on top or on the bottom. But on the left-hand side, there's an I, and there's an H bar, and then there's psi dt. And then on the right-hand side, there are other derivatives. But on the left-hand side, there was this I. Now, people were not ignorant in those days. They knew about complex numbers. They absolutely knew about complex numbers. And they would also use complex numbers in their calculations. Fourier transform, for example. It's very convenient if you use complex numbers. But they also knew that these were always intermediate steps. So whatever you do at the final, at the end, even if you've worked intermediate with complex phase factors, at the end you take signs and cosines. Because that's the world around us. So complex numbers are only allowed intermediate. You can never observe, even when we talk about electromagnetic fields, right? E and the B, these are real fields. And yes, it's very convenient to work with e to the I omega t and all kinds of, but these are intermediate steps. And somehow in Schrödinger's equation, it was not like that. The fundamental object there, psi, was complex. And Schrödinger was very well aware of this, and this is a letter which he wrote. I copied this here in particular because it's my predecessor. It's Hendrik Lorentz, who was in Leiden. And Schrödinger wrote to Lorentz, yes, I'm sorry for this imaginary thing. It will probably go away. It's a field in development. Certainly, in final analysis, will turn out that you have to take a real part. So I'm working on this. Psi is surely fundamentally a real function. And we know, we're 100 years later, we know it's not like that. Psi is still complex. And Freeman Dyson wrote this very eloquently. I would not be able to say it as nicely. And Schrödinger put the square root of -1 into the equation, and suddenly it made sense. Suddenly, it was no longer a heat equation, but it became a wave equation. And that square root of -1 means that nature works with complex numbers and not with real numbers. And somehow the theme of this article by Dyson was the question, is mathematics invented or does it exist in nature? So I'll be talking about Majorana fermions, some sort of new particle. And we know whether it has been observed or not, it's there. We did not invent the particle. But with mathematical concepts, it's more ambiguous. And you might say probably integers exist. Real numbers, not so sure. Complex numbers, certainly not. It's not for nothing that the name of the letter I is imaginary. Imaginary meaning non-existent. And somehow the theme of Dyson's paper here was that actually we're wrong. Complex numbers, imaginary numbers, existed in nature long before we discovered them because they're foundational for quantum mechanics. Now you might ask yourself, perhaps you've never asked yourself this question, why can't I just get rid of this? Why can't I just take real imaginary part? Well, here's the reason why. So let's write down this psi, and I write it as we always do with some harmonic functions. So there's spatial dependence, and there's time dependence, there's a wave number, and there's an energy. And you could do the same with electromagnetic waves, right? With E's and B's, electric and magnetic fields. And then energy would be frequency. Energy would be frequency, but that's it. And of course, there's also stuff. Well, you can have the plus and the minus here. The plus and the minus just means whether the wave moves to the left or moves to the right. So that's something you can get easily. This I can easily get rid of it. I just take a standing wave. We learned about this in class. Propagating waves, you have standing waves. Standing waves is position from which moves to the left and moves to the right. and then I get rid of this thing here. But now I also want to get rid of this thing, and that's more tricky because in physics, yes, you have positive and negative energies. Positive energies, that's let's say the usual particles, and the negative energies are called antiparticles. They somehow exist. They have a negative mass, something like that, something strange. It was Dirac who first invented. Why he thought he invented the antiparticles. He thought they did not exist in nature. And then we found that yes, they do exist in nature. Positrons. But this is a new type of particle, antiparticle. It's something else. And so, if you want to get rid of this complex number, you have to take the sum or the difference of this thing. Right? That's how you get real and imaginary part. The sum and the difference. But then you're making a superposition of a particle and antiparticle. That makes no sense. Even in quantum mechanics, it makes no sense. You cannot make a superposition of two different objects. Right? I mean, I can make a quantum superposition between electron and spin up or electron and spin down, but I cannot make a quantum superposition between an electron and a proton. That makes no sense. And so this is what prevents you from having a real wave function in quantum mechanics. It's the distinction between particle and antiparticle. And of course, with electromagnetic waves, it does not exist because electromagnetic waves are photons, and there's no antiphoton. Perhaps you've never heard of an antiphoton. You've never heard of it because it does not exist. There's no antiphoton. So the photon is the antiphoton. Actually, what is a way to find out that the photon is the antiphoton? Is because two photons can annihilate. Right? If I take an electron and a positron, and I bring them together, then they annihilate. They're done. If I take two photons and I bring them together, they can annihilate. You can create a photon, you can annihilate it. So you know that it is its own antiparticle. That's the test, the litmus test for something being its own antiparticle. Can it annihilate with itself? Electrons cannot annihilate with themselves. Obviously, because if they would annihilate, what do you do with the charge? Electron and a positron, yes, they can annihilate. No violation of conservation of energy, of course. If electron and positron collide, as they do in CERN, and they collide and the energy comes free, the particle goes on. And so for photons, you can easily do that. And that's why for photons, you have a real amplitude, electromagnetic field. And with electrons, you can't do this. Now, we know all these things. These are the things you learn if you follow a course in quantum physics. But 100 years ago, we'd never heard of this before. So this is very unusual. And so here it is. Here's our friend. One thing, let me interrupt for just a minute. So why don't you ask me questions while we go along? I'm somehow frightened to see all these faces staring at me. And so it's much more lively if you interrupt me and ask questions. And I'll just keep track of the time. I'll stop at 45 minutes. Whatever. So it's much more lively if there's some sort of interaction that you got there. It's also a bit intimidating. Okay, so please interrupt me as often as you want. Okay. So that's how it is. And
you would like to say that photon and antiphoton is the same particle?
Yes.
But what is the reason?
Well, yes. What is the reason? Well, this is actually a question which a physicist, an Italian physicist, Ettore Majorana, asked himself at the beginning of last century. So Dirac somehow made it seem like a mathematical necessity. You had a particle and an antiparticle, which were distinct. Now, if they have a charge, somehow you can appreciate that. If it has a charge, obviously particle cannot be antiparticle. Makes no sense. Photon has no charge. The photon is a boson. And with bosons, it's a bit more... bosons are classical, in a sense, classical objects. So the fact that the photon is the my answer to your question, why must the photon be the antiphoton, is because electromagnetic fields are physical observables. I can observe electric fields. So it must be real. There's no question about it. The electric field must be real because I can just measure it. And if it's real, it means that I must be able to make real superpositions. And so this is, but we sometimes call them classical waves. So the terminology for electromagnetic waves is classical wave. Classical wave is something which is real, so there's no distinction between particle and antiparticle. Now with fermions, it's different. Fermions are not classical waves. But Majorana, Mr. Majorana, Ettore Majorana, asked himself the question, is there some theorem which prevents that? Or is it just that we haven't found this particle, which is its own antiparticle? Is it just that we haven't found the fermion analog of the photon? And we still don't know. So we're a century later, and we still don't know if the Fermion analog of the photon exists. If it exists, it has a name. It's called Majorana fermion.
But do you make a statement that any boson is always there is no antiboson?
Yes, I think that's a statement. That's a valid statement. Yes.
So Higgs doesn't have antiboson.
Yes, I think that's a valid statement. But I mean, my knowledge of the big field of physics is kind of limited. I mean, I'm not some of the oracle who will give you, infallible answers to any question. But this is what I understand: the notion of particle distinct from antiparticle only makes sense for fermions. Anyway, this is so. Why am I talking about all this ancient stuff? It's interesting. It's 100 years old. Who cares? Well, why we care is because we found a way in nature to find. We found where we can find these Majorana particles, and we can find them in superconductors. And I'll slow go through the steps. But the first step is already this. There is an equation for superconductors. It's called the Bogoliubov equation, and it's a real wave equation. This is how it looks like. Or another way to put it, the Hamiltonian for Bogoliubov quasiparticles, that's how they call it, is purely imaginary. Now, those of you who have followed the course of physics know that Hamiltonians have to be Hermitian, but they don't have to be real. So if the Hamiltonian is purely imaginary, it means that it's antisymmetric. Because Hermitian means complex conjugation and taking the transpose. So if it's purely imaginary, that's okay, as long as it's antisymmetric. That's completely allowed. Usually it's not like that. Usually it's actually the other way around. Usually Hamiltonians are real. So usually it's precisely the opposite. They're real. So you have something real here, something imaginary here. But in the Bogoliubov equation, you have something imaginary here and something imaginary here. And of course, if you have an I on both sides of the equation, you just cancel it. So it's gone. So the Bogoliubov equation is a real wave equation, so its solutions are real. And so you cannot take complex conjugation. There's not this notion of particle and antiparticle. So presumably, Bogoliubov quasiparticles are Majorana, and yes, they are. Indeed, they are. But these statements which I wrote down here, this took a while for people to appreciate. In fact, it was only appreciated in the last couple of years. The prehistory goes much further. So let me show you a picture of them. So this is Majorana. Here he is. He looks a bit sad. Doesn't he look a bit sad? Doesn't he look a bit sad? And in fact, yes, his life was not without its difficulties. But he did some great stuff. I mean, if it was your son, you'd worry. You'd say, hey, kid, go out on the street, have fun, enjoy the beach. You would, wouldn't you? I would. But no, he studied and studied. He didn't publish, actually. He needed, because he was never satisfied with it. So he needed his friends to publish it for him. In particular, the Majorana paper was written by his friend Enrico Fermi, who was deeply impressed with Majorana. And if you don't publish, you don't get tenure, even in those days. So he had friends to write things for him. But that's okay. It was his big discovery. And this is Bogoliubov. He looks much more. No, I think he doesn't really smile, but he looks more. I think he does. Anyway, this is Bogoliubov. And so in particle physics, there is this thing they call the Majorana mass. So remember, why can't we take coherent superpositions between particle and antiparticles? Quantum mechanics would say you cannot make transitions between particles and antiparticles. That's a technical term we use. To make a superposition between two things, you have to make a transition. You have to couple. You cannot couple particle and antiparticle. It makes no sense. But Majorana found a way to do this. Majorana realized how he could couple particle and antiparticle, and this thing which couples it is called the Majorana mass. It looks like a mass, but it's a strange mass because it makes transitions between particles and antiparticles. And so there's actually a big effort in particle physics to measure the Majorana mass of the neutrino. Neutrino is charge neutral, so who knows? There's an option there. Right? I mean, electron will certainly not work. But neutrino is charge neutral, it could just work, it might just work. But, so you have to measure, and so this is important to realize. So there are all these experiments trying to detect, to figure out whether the neutrino is Majorana fermion. Now you might think, particularly if you read the popular press, you might think this is a yes or no question. Either it is a Majorana fermion or it's not Majorana fermion. But it's more subtle than that. It's not a yes or no question. It's measuring this Majorana mass. So you want to know how big it is. If it's non-zero, but infinitesimally small, then there will never be transitions, hardly ever be transitions. So you might even say, yes, it is a Majorana fermion, but it makes no sense because the transitions are too improbable. So you need, so it's not a yes/no question. It's a question of gradual question. You want to measure this Majorana mass. Same thing in superconductivity. So what is the analog in superconductivity of the Majorana mass? It's the thing which is called the pair potential. And those of you who have worked in superconductivity, and I'll show you a slide in just a moment, will know, yes, the pair potential couples electrons and holes. Somehow in metals we speak about electrons, but we don't speak about positons. Electrons we call holes. But it's ultimately the same thing. So yes, in the Majorana, the superconducting pair potential makes transitions between electrons and holes. And so it plays the same role as the Majorana mass. And also here, this thing could be zero, it could be almost zero, and then it's kind of irrelevant. It could be big. Now, how does this work, actually? Because you may be worried to say, well, hang on, neutrinos, they're neutral, yeah, that makes sense, but electrons have a charge. So what does it even mean to make a transition between things of opposite charge? It makes no sense. Well, now comes the trick. That's the big trick. So this is the C of, this is a superconducting, we actually use the word C, that's the word we use. So electrons in a superconductor are paired. They're paired in things which we call Cooper pairs. And the thing which Bogoliubov equation does not describe the Cooper pairs, they're like the C, it describes excitations in this Cooper pair. They're the only thing which makes sense. Excitation is a broken Cooper pair. So here is an excitation, so this is my particle, which is described by this Bogoliubov equation. It's in the C of paired electrons. Now I ask you, okay, please tell me, is this like a pair plus an extra electron, or is it a pair minus an extra electron? So is it a particle, pair plus a particle, or is it the whole, pair minus a particle? Well, there's no way you can answer this. How could you possibly answer this? It's like somebody giving you a glass which is, say, please tell me, is the glass half full or half empty? It's a question which has no answer. And because it has no answer, quantum mechanics says, okay, if there's no answer, then I'll just freely make transitions between them. So I can freely make transitions between particles and holes. Now, of course, there is an approximation here. There's an approximation. Give you the total system, big piece of metal, superconductor, 10 to the 23 electrons. Yes, you'll be able to say, has this number increased by 1 or decreased by 1? So I start out with everything unpaired, and then I add 1 or subtract 1. That's certainly a valid answer. But as you can imagine, it's not a very practical answer, and in practice, this difference does not appear. So the difference between Cooper pairs plus none or Cooper pairs minus 1 typically does not appear simply because there are too many Cooper pairs. So in very good approximation, yes, you can make transitions between electrons and holes. That's what the pair potential does. The pair potential breaks up pairs or forms pairs. So if I have another one of these, if I have another one here, and the pair potential will bring them together in pair. And that's how it works.
Maybe this is a good approximation if you compare one particle to the rest of the system, not locally.
Yeah, but you see these are metals. So they're not localized, they move everywhere. And so it's like a droplet in the sea. If you go to the sea, there's a sea here, right? You go to the sea, and you disperse a little bit of ink or whatever, or put a little spit in the sea. And I say, yeah, it makes a difference. Locally, I can see my spit here, perfectly, it's gone. And so, yes, there are approximations, and it's interesting physics to try and study all of this stuff, but in first description, these are big pieces, it only works in big pieces of metal, microscopic systems. And then, basically, it's going to be relevant. You don't see it. It's delocalized, it's gone.
But next question, excitons and Cooper, do you have exciton?
Or exciton is a boson. It's an electron plus it's a particle whole pair. So that's a boson. That's different. That's in this bosonic category. So when I say I mentioned explicitly, I said coherent superposition. So it's one particle, which is think of Schrödinger cat. It's one cat which is in superposition of alive and dead. It's not a dead cat here, a live cat here. That's something completely different. So exciton is in a sense a classical object. It's just an electron a positive charge and a negative charge abound. Maybe quantum effects, but there's no real way in which this plays a role. It's really a different thing. No relationship at all. Okay, so yes, it's for neutrinos we don't really know whether they're Majorana, who knows? But in superconductors they exist. They've always existed. And they've always existed. This particular sentence here has always been true, but we have only appreciated it now, just in 1 or 2 years. No, it's not completely true. It was the first people to appreciate this is already 50 years ago. So I actually went back in time and I asked myself, how far should I go in time before somebody realized this? That superconducting quasi-particles were Majorana fermions. Majorana lived in the 1930s, Bogolyubov worked in the 1950s. But, okay, so these are the two earliest papers. They're published in 2000, but they were submitted to the archive very shortly after each other. In the summer, this is 6, right? So that's in June of 1999. These are the earliest papers who discuss, here they talk about Majorana metal, who discuss quasi-particles in superconductor as being Majorana fermions. Majorana fermions, edges, vortices, metal. So it's not so long ago. It's not so long ago. And some of the effects, which were, actually most of the effects which were predicted in these papers have still not been observed. So there's a whole string of theory papers. We've made some experimental progress, little. I'll tell you of some of the experimental progress. So there's been some progress, not zero. But most of the progress has been theoretical. And that's a bit unfortunate, of course, but the field is moving. And so we'll get there. So what is one of the, this is actually a prediction made in this paper. That's this thing which is called the thermal quantum Hall effect. I'm not sure whether, who is familiar with the quantum Hall effect? Just two. You told me, no, they're all physicists, and then it's actually, it's not quite like that. Okay, just two. Okay, that's it's good. I actually prepared, you may have noticed I had announced a different title. The title of my talk was different, right? Then I heard here, yeah, they'll be physicists, but it's still maybe a bit rusty, the physics. Okay, so no, it's okay. So I'm giving a more tutorial talk, which is perfectly okay. Perfectly okay. Anyway, quantum Hall effect, Nobel Prize, 1985. European Nobel Prize, Auschwitz, another Nobel Prize, whatever, in 2000, I think, Sui, Laughlin, so 2 Nobel Prizes for the quantum Hall effect. Quantum Hall effect is you take a piece of metal, it's a semiconductor, put it in a magnetic field, and then electrons move along the edge. This is what they like to do. And they have a quantized conductance. And this is also one of the few applications of all of this nanophysics, because the conductance is quantized to as many decimal places as you want, and so it's being used already commercially as a resistance standard. The resistance is 23 point so many kilo ohms. It's something which you can measure with unprecedented accuracy, as much accuracy as you want. So that's a resistance standard. So it's even a practical effect, which is at this moment the only commercial application of graphene. So there is this European graphene flagship. I'm actually involved in that for some reason. And this is 1 billion EU euros. It's our money. That's our money, which went into graphene because somehow this would then, be a disruptive technology for Europe. There's one application. Well, no, it's good. It's better than zero. and this is because graphene has quantum Hall effect at room temperature. That's very convenient. You can have a room temperature. There's a box you can buy, and then you can just measure. It tells you the resistance with many decimal places at room temperature. So now this is the analog in a superconductor. Now the analog, so these are edge states. Here they move. These are Majoranas. These Majorana fermions move along the edge for the same reason that electrons move along the edge in a normal metal. Now these Majorana fermions have no charge, right? They cannot have a charge. They're coherent superposition of electrons and holes, so they're neutral. So we're not talking about electrical conductance. That makes no sense. They don't carry any charge, but they do carry energy. And energy, that's what you measure in heat transport. So instead of a quantized electrical conductance, you have a quantized thermal conductance. Now unfortunately, does anyone know what is the quantum unit of electrical conductance? Yeah, the little prize, and someone's making notes here. I think also credits for these things. So, unit of quantum unit of conductance. So something which has the dimensions of conductance and which involves only fundamental constants. Anyone? Yeah.
E squared over it.
E squared over h. That's right. So it's a kind of a memorable thing. Each over h is memorable. Now, unfortunately, the quantum unit of thermal resistance is miserable. One is memorable, the other is miserable. Here it is. That's the quantum unit of thermal conductance. Yes, it's miserable, right? With the pi squared, it's at 6. And actually, if you look at Wikipedia, it will tell you that the quantum unit of thermal conductance is 3 here instead of 6. 3, no 6. That's important. Why is there a 6 here? It's because a Majorana is actually only half a Fermion. You know, because a Fermion is a complex object. It's a complex object. So if I give you a wave function of a Fermion, it's a complex wave function. And I only have the real parts. I mean, this is of course not the mathematical way to prove it, but it's a hand-waving way. In a hand-waving sense, a Majorana Fermion is half a Fermion. Hand-waving sense. Half a Fermion, and the way to measure this half a Fermion is that the thermal conductance carried by these edge states has a 6 instead of a 5. So this would be a heroic experiment. If somebody would do this, this would be absolutely amazing. And there are several reasons why it has not been done, but it may be done in the near future. It's certainly one of these experiments, which will get a Nobel Prize, but it's one of these absolute textbook heroic experiments. The quantum with the 3 has been measured many times. You don't need electrons for that. You can do it with phonons or whatever. Quantum with the 3. The quantum with the 6 has never been measured. And yeah, one of the reasons is that heat conductance is just very hard to measure. You know, if you want to measure electrical conductance, you go to any shop and buy a resistance meter, right? You probably have, all at home have a resistance meter. I mean, I have like 2 at home. I measure some short somewhere. I go to a shop and say, could you give me a thermal resistance meter? They'll look very strange at you, right? And they say, sorry, we don't have that. So even in the ordinary world, room temperature world, heat resistance measurements are not easy. And now you want to do the millikelvin temperatures, whatever, so it's absolutely. So this is, I'm not saying it's impossible, but it's so this is one reason. And some of the research which I've been doing in the last year or so is to come up with a way to do these experiments without purely electrically. And I'm probably going to skip over this. So this is just some recent paper, and I'm writing another paper along these lines at the same moment. But some of my research projects at this moment are how can I measure this thermal conductance purely electrically? The thing is, and I'll just tell you the key ingredients why it's possible. The key ingredient is this. So when I said the Majorana Fermion is charge neutral, it's true. It's charge neutral. However, it is not, say, in an eigenstate of charge. It's a quantum superposition between plus and minus. So when we say charge neutral, we mean the expectation value of the charge is neutral. The average. With their fluctuations, quantum fluctuations of the charge. So Majorana Fermion has quantum fluctuations of the charge. And in fact, let's try to calculate, just as a little exercise, calculate the quantum fluctuations. Well, that's not so difficult. Right? Because it's charge plus E with probability 1/2, it's charge minus E with probability 1/2, right? So the average is 0, and the variance is 1. So they have quantized, they have 0 charge. An electron has 1 unit of charge and 0 fluctuations. A Majorana Fermion has 0 units of average charge and 1 unit of fluctuations. So if you want to measure electrically this Majorana Fermion, you shouldn't be measuring the average current, it will always be 0. You have to measure the fluctuations of the current. You might say, I've never heard of that. But that's actually something, you might even be able to go to a shop and it will sell you this thing. It's called noise meter. I mean, anyone who's in physics will know that this is important to measure the noise of some resistor. Please tell me what's the noise power of this resistor.
But the superposition, you assume they have the same weight?
Yes, they do.
But why?
Oh, this is a property of the problem which is called particle hole symmetry. So if I'm at the Fermi level, I have to add this, but I will. So if I'm at in superconductivity, there's this notion of the Fermi level, it's a special energy, and all states are symmetric along that energy. This is a property of well, it has much to do, of course, with this thing, with this little plot here.
But the modalical transformation you prefer arbitrary.
Yeah, but not at the Fermi level. Yes, but if you insist that you have a state at the Fermi level at E0. No, this is. In fact, you can easily see it from this property here. Hang on, just a moment. here it is. I have it. I'll just go. I have to find it. Here it is. So if this is your H, then H star is minus H. H star is minus H. If H star is minus H, it means that the spectrum is plus or minus E symmetric. If the spectrum is plus or minus E symmetric, if you're at E0, any wave function you write down will have equal electron hole contents, not anything else. So this is it's a property of the, it's a bit of an advanced property, but it's called particle hole symmetry. Particle hole symmetry guarantees that they have equal weight. And here it is. And okay, so this is some work I'm doing. So this is actually the statement. Majorana mode has a quantized sharpness of 1/2 times E squared raised per electron volt. The conductance is 0. The sharpness is 1/2. Again, the 1/2 is the same half fermion. And so this is an experiment which I'm trying to promote. And who knows, someone will do it. Now, I'm probably going to skip over this. Yes, I am. This is important. And I just want to show you. Yeah, this is good stuff, but I'm going to skip over it. And I want to show you an experiment hunting for Majorana fermions. So somehow this whole thing with these edge modes and this has not been done. I mean, it may be done, but it's not been done. And people have tried something else. That is to bind a Majorana fermion somewhere in space. At least there it's stuck. It's what you might do with a particle, right? Perhaps the particle is flying and you have to find it, but it would be good if you could just trap it, right? Give you a box, here it is. And you could try to do that. And one way to do that is, so here's my superconductor. And for a reason which, I mean, I could go, it's really very much fun to explain this, and there's lots of recent people who have contributed to this, who will now be watching the YouTube video and say, why doesn't this guy tell them that I did it? I mean, this particular person did it, but I'm not going to do it. I'm going to skip that and just tell you that, so what we've discovered over the last 10 years is that if you have a superconducting wire with sufficiently sophisticated properties, there will be a Majorana fermion bound at the endpoint. Here it is. Here's a trapped, and there's a barrier here. So this geometry, this is an actual experiment. Indium antimonite, why indium antimonite? Because you need spin-orbit coupling. Indium antimonite on top of the superconductor, why niobium? Because it needs to support the magnetic field. And most superconductors die if you have a magnetic field without niobium. This particular system, theorists told us in 2010, this system has a trapped Majorana fermion. It was probably the first, experiment which was so realistic that people said, I have this object in my fridge at this moment. Because if you just look at this device, it doesn't look like a completely exotic device. You can imagine there are many groups who are working on a device which is very similar. Wire, superconductor, barrier, whatever. Indium antimonite, indium arsenide are also very conducive materials. They're materials which people like in the lab because they grow very simply. I mean, they're fun materials, not expensive, not poisonous. They're garden variety materials. And so when in 2010, Oreg and Luchin, Sau, and Sarma, and Oppen wrote a bunch of papers saying this is the system which will trap a Majorana fermion. The whole experimental world will this. It doesn't happen that often. People, theorists propose experiments all the time. You guys, and most of the experiments we propose are wildly unrealistic. Not even someone will not even begin to try and do it. Pretty much every experiment we propose is unrealistic. But this was an experiment. Not only was it not unrealistic, it was something where many said, I have a student. I'll ask him to do it next week or next month. And this is what happened. And so the race came to find this Majorana mode. And how will you see it? Well, you see it in the same way that you see particles in particle physics. How did they find the Higgs boson? Someone mentioned the Higgs boson here. Some little peaks, some resonance peaks. You do some scattering experiment, and there are lots of peaks there which you can explain. And then there's one peak which you cannot explain. And you can say that's it. Then, of course, you have to convince the rest of the world. That takes time. And it worked in exactly the same way. So here is the experiment. So this is the current. So they tried to send the current. Here says I. You see, trying to send the current to this device. This is current. This is already the latest data, 2016. The first experiment was published in 2012. The experiment has improved. This is the latest experiment, and there are many groups with similar data. So if this experiment is wrong, it's not wrong because it was some artificial thing. It's wrong because we haven't understood what it's telling us. The experiment has been repeated by a whole bunch of groups. And it always looks the same way. So here you have currents, the IDV, so it's current divided by voltage, units of 2 squared array. Here there's applied voltage. And the different traces, they're all at different magnetic fields. They're all on top of each other, of course, but just to make sure that there's something to see, they've all been displaced. And so you see when you have zero magnetic field, zero touch line. Zero magnetic field, there's nothing. And then as you apply magnetic fields, a peak appears. At zero energy, that's where the Majorana fermion lives. Lives at zero energy. Zero energy means fermion. That's where it lives. And so it's there. And there are good reasons to expect theoretically that you need a magnetic field to stabilize it. So there are good reasons to expect theoretically why it only appears in a magnetic field. And that's him or her. Or probably them, right? Because if it's anything, then it's gender neutral. You think so? I think so. Okay. So why haven't you heard about this? Prizes, whatever. You know, everybody's shouting, we've seen it, we've seen it, we've seen it. There are basically two reasons why it's problematic. One reason is that theory tells you that the peak should be 2 squared range. You know, this fundamental problem. And the peak is only, even now, you know, 5 years later, it's only 0.1 times 2 squared range. We don't really understand why it's only 0.1. That's one. It's bad. I mean, it's quantized. It should be quantized. You say it's quantized, but it's quantized with 10%. No, it's quantized, but it's factor 10 too small. So that's not good. It's not helpful. And the other is that the width, and this is very low temperatures, the width should be given by temperature. It's the only thing which can give you a width. It's a resonance. The only thing which can give you a width is the temperature. But it's 15 times too big, too wide. So the combination of these two things suggests to skeptical people may very well be something to do with it. And I'm not part of the skeptical people. I think this is the Majorana, but I also do not have a reason why it's not. So the field is a bit. So actually what's happened in the last 5 years, it was 2012, so there were like 4 or 5 years of people trying to improve this experiment. It's not improved. It's not improved. So what do? You continue for another 10 years trying to improve it, or you say, well, I'm going to move on. I'm just going to assume that it is a Majorana, I'm going to use it. I'm going to do stuff with it, make a company that sells it, make money, and then all these other people will be telling you, sure, but it's not a Majorana. Okay, so, and this is happening now. So what can you, so the field has moved on from you know, let's convince the rest of, there will always be skeptical people who do not believe that it's a Majorana. Okay, that's their problem. We admit this is ugly. I wish it was different. It's not. This is what we have. This is what we have. Can we still do something with it? Or are you going to tell me no, because it's so wide you cannot use it for anything? So you might ask, what am I going to use this Majorana for? How can I build a company on Majoranas? Well, you can. And this will be
one question here. These peak, height, and width, there are no explanations for this phenomena, or there are many possible explanations?
It could be a peak due to some weak localization, weak anti-localization type of peak. There are many mechanisms which, see, there's actually only one mechanism which gives you a quantized state. But there are many mechanisms which give you non-quantized states. Weak anti-localization, Kondo effects, Coulomb blockade. But of course, then you're experimentalists and say, no, I have ruled this out.
No, but my question is, even assuming that this peak is from Majorana, the possible origins of this peak
I don't really know. I do not have a real explanation. So in the final, I spoke now for almost 40 minutes. I can speak for another 5. So what are we going to do with this thing? So, part of the excitement in this business is not so much have you seen the Majorana, have you not seen the Majorana. If we have it, then it's a gift to mankind. We need it. In this time and age, we desperately need it. This is a gift to mankind. Why is it a gift to mankind? And this will bring me back to actually how I started, about the absence of complex numbers. You have a wave function which is real. Now, there's something in physics that if you take fermions and you exchange them, then you can pick up a phase factor. This is a fundamental thing. I mean, it's a complex wave function, so who says that if you exchange them, you might say if I exchange them, then the system is back to where it started. Yes, but the phase factor is not observable anyway. Since it's not observable anyway, there's nothing to prevent quantum mechanics from giving you a phase factor. And I find it easiest, I can do it in terms of wave functions, but it's actually slightly more convenient to do it in terms of operators. If you've had a quantum mechanics course, you know that these are two Heisenberg picture and a Schrödinger picture. So I find it more convenient to talk about operators. So here I have one Majorana, which is operator 1, and another Majorana, which is operator 2. So these are like the fermion creation annihilation operators, with one difference. For the fermion creation annihilation operators, we would write something like A for the annihilation operator and A dagger for the creation operator. Perhaps you've seen these symbols before. They're different because to annihilate something is different from to create it. But if a particle is an antiparticle, obviously there's no difference between creating an antiparticle or annihilating it. It's the same thing. And so these gammas are actually Hermitian. So the gamma equals gamma. They're real operators, real Hermitian. Okay, they're real. Now you exchange them. Now if you exchange something and it's real, the only phase factor you can give it is plus or minus 1. There's no other phase factor. If I give it the complex phase factor, then I break this, of course, right? Give it a complex phase factor. So I can only, I can have plus or minus, or I can have, in principle you might say I can have also plus or minus here, who knows? But now I'm going to tell you there's a very fundamental reason. If I have a plus here, then I need to have a minus here. And if I have a minus here, I need to have a plus here. Why is that? This is because there is actually a physical operator. These gammas are not observable. But there's a physical operator which is observable. That's the number of electrons. It's actually the parity of the number of electrons. And this physical operator has to be a Hermitian operator. What is this Hermitian operator? It's this guy. It's I, gamma 1, gamma 2. Why is it Hermitian? Well, it's Hermitian because these are fermions, so if I exchange gamma 1 and gamma 2, I get a minus sign. And I have an I here, so that's indeed a Hermitian operator. And I'll tell you, this is something that you have to convince yourself, but this is the operator which counts whether you have an even or, it has two eigenstates. Square is 1, so its eigenstates are plus or minus 1. Its eigenvalues are plus or minus 1, and its plus 1 is the even number of electrons, and minus 1 is the odd number of electrons. Now, obviously, interchanging two Majoranas is not going to change the parity of the number of electrons. That's ridiculous. So, if I interchange these things, so I go to I, gamma 2, gamma 1, that should be the same. But it's not the same because they're fermions. So this interchange has to give me a minus sign. And so if I said that this thing was the plus sign, then this thing has to be the minus sign and the other way around. I cannot have plus plus and I cannot have minus minus. So this is called, it's called statistics. It's called braiding statistics because of this motion of moving things around. It's called braiding. And it's called non-abelian because now actually the order matters. The order matters. Because I have here written it down in terms of the operator. If I have many operators, because of the strange thing that I have to decide which one gets the plus and which one gets the minus, if I have a whole bunch of them, it will matter how I interchange. In the same way that if you've ever braided or knitted, you put things, the order matters. The order matters a lot there. What do you put on top first, and then this, and then that. It's like making a knot. The order matters. So this is called non-abelian braiding statistics. This was discovered by Reed and Green in 2000. And this is actually what the field is waiting for. The field is waiting for someone to demonstrate non-abelian braiding statistics of Majorana fermions. Because then the rest of the world will shut up. Because then you have this little peak could be anything. But if it has this strange non-abelian braiding statistics, that's it. I haven't told you yet how to make money out of that. I've told you how to start winning prizes. That's the first thing. And Kitaev, 2003, this was 2000. Kitaev in 2003 came up with a way to make money out of this. And in fact, he already earned money out of this. He earned $3 million. How did he get this? He won the fundamental physics prize for this idea. This wealthy competitor of the Nobel Prize. So what was his idea? So you may have been exposed to quantum computation. Have you been exposed to quantum computations? So the thing about quantum computation is this. A quantum computation, which is an abstract person, a quantum computation is a sequence of unitary operations acting on a wave function. That's it. A sequence of unitary operations on a wave function. And somehow we've discovered that the way we conventionally do computation, which is with binary operations, zeros and ones, has less computational power than unitary operations on a wave function. mean, it's not trivial, and computer scientists are still struggling with this, but this is somehow what we believe. We believe that unitary operation on a wave function has more computational power than binary operational powers. Now, I haven't written you down the unitary operation which corresponds to this, but I could. I mean, this is just a symbol. The unitary operation, U is e to the I pi over 4 sigma x. If you've never seen Pauli matrices, it won't mean anything to you, but that's the unitary operation which corresponds to this. In this unitary operation, what's special about the unitary? There's so many ways to make unitary operations. What's special is that the pi over 4 is exactly all decimal places. It comes from this plus. See, there's no ambiguity. If I would tell you this is some phase factor, some e to the I, whatever, you say, well, perhaps it's not. It's almost at phase factor. But if I tell you this plus or minus 1, I mean, what error can you make? I mean, it's exact to all decimal places. And because this plus or minus is exact to all decimal places, the pi over 4 is exact to all decimal places. This is called topological quantum computation. The word topological comes from this whole Braiding thing. It's jargon. What we mean is that we're doing a quantum computation in a way which is not sensitive to errors. This is the big problem of quantum computing, sensitivity to errors, for which we have to correct, which is absolutely miserable. Absolutely. And this gets away with that. It gets away with the need to do error correction. And that's heroic. And there's one company in particular which is betting, not the bank, much of its credibility, but that's Microsoft. So Microsoft has embraced quantum computation already a long time ago, has embraced it, and is betting on this particular way of doing it because it's insensitive to errors. And its competitor Yahoo, this could be Google, its competitor Google, says, we'll just do the conventional way, we'll just be very careful not to make errors. No, these are two different strategies. You don't really know which one will arrive first. They're two completely different strategies. Just avoid errors, or have a scheme which by definition is insensitive to errors. It's unclear which one. Certainly intellectually, this one's much more fun. This one's, I mean, it's much more fun to do it in this way. This is what I'm doing, in my daily work. It's much more fun to try and do it in this way than just instruct your graduate students, please make no errors. Very careful. But being more fun does not mean that it will arrive first. So this is probably it. This is my last slide. So what am I doing actually? So this is all fun, but it's kind of like mathematical stuff, right? Read, green, diagram, essentially mathematical physicists. So now I have this lab. It's not my lab. It's the lab of my collaborator, Leo Koutman in Delft, and they want to do this. So now we need someone to translate these mathematical concepts into something which you can then go to a student and say, please do this, right? I can assure you, you cannot go to a PhD student in experimental physics and say, please pick up your Majorana and pick up the other one here and interchange them. No, it just makes no sense. No one will ever do it in this way. This is the way we describe it conceptually. So somewhere now you have to go back, step back and say, what do we actually mean when we do this? Can you somehow interpret it in a language which will be much less fun, much more technical, much more sample specific, but which makes sense? And that's this design here, and it's Josephson junctions, there are fluxes, there are wires. It's ugly. I cannot really tell you here what I'm picking around and moving around something else. It's not like that, but it does the same thing. So it's quite often it's like that. There's math, which is beautiful, and then you translate it into something which works, and then you don't no longer recognize the beautiful thing. But it does exactly the same thing. This is what we call the blueprint. It's already 3 years ago we published it, and we're getting close. Well, my friends in Delft are getting close. So this is. It looks like an artist's impression. It is in a sense, but it started from an SEM photograph. So this is actually, honest to goodness, something they have in the fridge. And you see they've made these junctions. These are the superconductors. They make the junctions, and here are the wires. So the wires here, and they're getting there. And they give themselves a couple of years to do this. Lifetime of a PhD student. That's it. Lifetime. No, I mean, but you see, take gravitational wave detectors. That was 40 years, 50 years. There are not that many experiments which are heroic and which you can imagine doing within the lifetime of a PhD student. Not that many. This is one. This is one. You cannot guarantee it, but most people will agree that if you do this experiment and it's convincing, you get a ticket to Stockholm. Why to Stockholm if you can go to Mallorca? There's some reasons for going to Stockholm. There's some reasons for going to Stockholm. No, this is the truth. And And I will not be there, perhaps I'll be there as a guest, but I will be there applauding them. That's my job as a theorist. Okay, so this is the end, and this is my last slide. So I've tried to convince you by some examples, I could give many more, but I'm not going to do that, yes, there is lots of fun if you do quantum mechanics, even complexities if you do quantum mechanics without complex numbers. Thank you.
Comments or questions?
So this thermal quantum Hall effect with Majorana's, one edge is hotter.
Yeah, you make one edge hot, the other edge cold, and you see, you can do two ways. Either you make one edge hot, the other edge cold, and you see heat current moving not along the gradient of the temperature, but perpendicular. Or you send a heat current through it, and then you find a transverse temperature difference. It's exactly what you would do when you do electrical conductance. But just translate electrical current to heat current, and translate voltage difference to temperature difference.
And of course there would be no thermoelectric because there's no charge there.
Yeah, no thermal electricity. It's symmetric. Everything is symmetric, so there's no thermal electricity.
But there is a thermal diffusion due to thermal gradients.
Well, so the problem with thermal electricity is lots of fun. And there are even some works people have tried every permutation with Majoranas. So you take your favorite topic, you say, let me sprinkle in some Majoranas. Professor Beenakker said it was a gift. Why can't it be a gift for you? It can be a gift for you. So you take your favorite project, sprinkle in Majoranas and see what it gives you. So also in the case of thermal electricity, yes, it has been done. So there are papers on thermoelectric effects involving Majorana fermions, and typically what you need is a three-terminal geometry. So for two terminals, particle symmetry kills everything. But if you have three-terminal geometry, you're in luck. So I even have some papers on this myself. And so yes, there's some fun things to do with thermal electricity in a three-terminal geometry. Nothing which will improve figure of merit or whatever, but it's kind of ingenious and interesting to think how this charge neutral particle can modify thermoelectric transforms. That's an interesting question. This was the question.
In this experiment of the thermal transmission by Majoranas, with its Majoranas, do you think it have some?
Well, okay. So here's the so one have different. So this is one problem which actually, right? Here I have a quantum dot. It has a fixed Majorana, and now I can, for example, apply a temperature difference between these things, or see what voltage appears. This is a problem. This is not an experiment which has been done. This may be done at some moment. It's not been done. This will be a fixed Majorana because it's bound here. And the previous one here you have things which move. So these are two different. They're really different things. Majoranas which move or Majoranas which are fixed. They're very different. In fact, we try to use a different terminology. We call this a Majorana fermion, and we call this a Majorana zero mode. In fact, you'll see in modern papers, they will try to avoid mixing these concepts because they're really very different things, and it's confusing to use the same name for both. So we would call this a zero mode. It's just that zero mode, in particular for a non-technical audience, doesn't sound very. In fact, for a non-technical audience, I wouldn't even use the word fermion. I would say Majorana particle. And so there's some jargon, like in any field. There's jargon, and we're slowly understanding most of these things.
Comments or
Just a curiosity, we were telling that topological is maybe a way, topological computation would be a way to make more of this. And then before you were showing this, there is this width of the peak. Is there any consequence of
Oh
this
yes,
width
it would be a
that is
disaster.
like
So it's because all these braiding operations, they take time, and this width translates to lifetime, and so it is. I would say perhaps no. The experimentalists are just going ahead. They don't care. But I would, as an outsider, I would say it's very unlikely that anything will come out of this because the lifetime of the thing is very short. But I will tell you, and in particular, there's not just Leo Kouwenhoven in Delft, there's Charlie Marcus in Copenhagen, who are just saying, well, we'll just go ahead. I mean, we'll see what we get. theorist tells it cannot be done, do this, do that, wait another 10 years, whatever. It's time to move on. And sometimes, you know, things work in this way. You just don't listen too much to people who tell you it can never be done. You just do it. And then if it works, somehow, you know, we had in graphene. Lots of papers tell you there's mathematical, fundamental physical reasons why a single layer of carbon cannot be stable. It will roll up, whatever. And Geim did it. And then the theorists come, yes, but actually it's not completely two-dimensional. There's ripples, and these ripples stabilize. Okay. So there's something, you know, this is actually why I'm, you know, I like to interact with experimentalists, but we should not be too close. They should be, it's like, no, really, it's like your children. You want to keep track of your children. You should not be too close on them. Just let them go out, explore, make their own errors. It's like that, right? Isn't it like that? I think it is like that. So they just go ahead, and I applaud them. And if they're successful, I think this is helpful.
So about spin, I mean, that doesn't
yeah.
play any role.
So all of these systems all of these systems have strong spin-orbit coupling. So spin is there, of course, but it's not. It's coupled to orbit, so it's not a good quantum number, if you wish to speak of it in this way. So this Majorana fermion is not an eigenstate of any spin. It will depend also on local details, but yes, it will have some expectation value of the spin. Why not? It must have. And so these are not spinless. Even the neutrino, you know, there's some of this misconception that Majorana fermions have to be spinless. Think about the neutrino. It has a spin. Spin 1/2. So yes, it has a spin. It's not an eigenstate of spin because of spin-orbit coupling, but it has a spin. And there are proposals to use this spin to get extra information out of this whole thing. It's absolutely.
There are no more comments, so we can thank Carlo again for it.
Okay, so I hope this was the right